So we have done up to this. Screen is visible.
Yes.
Visible, right? Okay. Just a minute. Okay, so any doubt from the previous class? Any doubt you guys have from the previous class? Any doubt you guys have? No, right? Okay. Fine. So today we will start Sharpless asymmetric dihydroxylation. We have started dihydroxylation topic, right? So today we will start Sharpless. Okay, Sharpless asymmetric dihydroxylation. Okay, so again I am saying, okay, I am not discussing the mechanism for this Sharpless thing, okay, because this mechanism is very difficult and it is time taking. Okay, it will take at least half an hour to discuss the mechanism only. So if you are interested, so you just visit your Claydon or Carothas book you have. Okay, if you have Claydon or Carothas, if you have PDF also, that is also fine. You just go to the last page. Okay, so in the last page, basically like your dictionary, you will get some alphabets A to Z you will get. So there you just search from in S. Okay, if you go to S, there you will get the Sharpless asymmetric dihydroxylation or Sharpless epoxidation. Okay, the both the things you will get there. So you just go there and check what is the mechanism. Okay, mechanism is actually very difficult, and what I can say, uh, that is not that much important from your for semester exam. It is important. Okay, when you will do in uh, PhD coursework or MSc, that time it is important, but for NetGate they will not ask the mechanism. Okay, they will ask only the product. So I am writing simply. So what we have, so initially we have this. Okay, you have double bond here. So here you have R double bond, and suppose here you have R triple bond, so R triple dot. Okay, so this is the alkene molecule, and all the alkyl groups are different here. Now basically here we have two kinds of reagents. Okay, so one reagent is this DHQD. Okay, DHQD, and with this reagent you will add osmium tetroxide, OSO4. So this is one reagent, or you can use another reagent that is actually known as your DHQ. So these are the two reagents you have. One reagent is your DHQD and the other reagent is your DHQ. Okay, so these are the two reagents we have, and depending on the nature of the reagent, which reagent basically you are using, you will get your product. Okay, so for one time you will get like this. Okay, for one reactant you will get both the OH in above the plane. Okay, and another will be like that. Another will be like that. Here both the OH will be in below the plane. So basically the stereochemistry is important in these questions, and it depends totally on the reagent, which reagent you are using. Okay, which reagent you are using. So again we will see here one trick. Okay, like in Sharpless epoxidation we have used what, red wall lal diwar, right? So here also you will use a trick. Okay, so basically This is the trick we will use. So here how to use, so see, so suppose you have this double bond, so here suppose you have small group, here you have medium group, and here you have large group. Okay, so you have to identify which alkyl group is your small, medium and large, that you have to identify. Now the first point you have to remember that small group, okay, small group should be, small group should be at left side, small group should be at left side. Okay, this is the first thing you have to do. Small group should be at left side, not in the right hand side. So in right hand side you no need to identify the small group, you have to identify the small group in the left hand side of the alkene. That is the first point you have to keep in mind. Number two point, you have to move like this, small to medium to large, like that you have to move. Okay, you have to move like this, from where to where, small to medium to large. Okay, now if you get clockwise, okay, if you are getting clockwise rotation, okay, so now it depends on the reagent. So suppose you have DHQD, okay, DHQD, so that will give you top, so that means wedge. Okay, and if you have DHQ, that will give you bottom. Okay, so basically you will get like this. Okay, now how I remember like this. Okay, so DHQD, so that means you have more number of letters, right? So you have 4 letters here in this DHQD reagent, so that will occupy high space, so that means top space. Okay, top place, so that means above the plane. Okay, so if you have higher number of letters, that will occupy above the plane. If you have low number of letters, that will occupy below the plane. Okay, like that you can I remember like that. Okay, so you can remember like that also. If you have more number of letters, that will go to up. If you have less number of letters, that will go to below. Okay, so this is only applicable when you are getting clockwise. Now the third thing, or this is not actually separate, this is not third, or you can mention it third. Okay, but the thing is anti-clockwise. If you are getting anti-clockwise motion, then what will happen? So if you have anti-clockwise motion, that time it is ulta. Okay, similarly it will be what, if you have DHQ, that time you will get above the plane, and if you have DHQD, then you will get below the plane. So you just remember for only one, you just remember for clockwise, anti-clockwise automatically you can do. Okay, so first point is what, first point you have to keep in mind that small group should be at left side. So you just identify the small group from the left hand side, not the right hand side. Okay, second thing, you have to move from where to where, small to medium to large, that you have to move. Third thing, if you are getting clockwise motion, okay, clockwise motion, so what I will check, clockwise motion. So if you have DHQD, so that means more number of letters are there, you will get top. Okay, if you have less number of letters, you will go to below. That's it. Anti-clockwise, it will be opposite to that. That's it. Okay, that is the trick you can use. Now if you see here, suppose you have small, medium, large, so you have to come from, sorry, you have to come from where to where, you have to move from small to medium to large, right? Small to medium to large. So that means what, which motion it is, clockwise or anti-clockwise? hmm? Which motion it is? Anti-clockwise, right?
Anti-clockwise.
Anti-clockwise, like that you have to check. Okay, uh, suppose you have like this, small, here you have large, here you have medium, so you have to go like this, small to medium to large, that time you are getting clockwise motion. Okay, like that you have to do. Suppose you have like this. Suppose medium group is there, small group is there, large group is there. So again, small to medium to large. This is what? And what? Clockwise, right? Clockwise. So like that you can do. And one point you have, this is the last point, number 4, that if can't decide, so you are not able to decide. Okay, if can't decide, okay, that we will see. So that time you have to follow clockwise rule. Okay, if can't decide, that time you have to follow clockwise rule. Okay, done. Done.
Done, sir.
Okay, write it down. If not done, write it down, all of you. Done, right? Okay, now suppose you have this. So here I have double bond. Okay, so here I have double bond. Now suppose I am giving this reagent. So here I am giving 0.2 mole percentage K2 OSO4. Okay, so this is your potassium osmate salt. Okay, dot 2 water. Okay, and you are using 1 mole percentage of DHQD whole 2, okay, PHAL. Okay, PHAL. With that you have K3 potassium ferrocyanide FeCN whole 6. Okay, you have K2CO3 potassium carbonate. Apart from that you can use Me2. This example you will get in your Carothers book. Okay, this example you will get in your Carothers book, you can check. Okay, tertiary butanol 0 degree centigrade. Okay, 0 degree centigrade. So what is happening? So if I am writing here DHQD whole 2 PHAL, so basically what is that? This is your dimer. Okay, so this is your dimer. So write down forms dimer with what? With DHQ and DHQD ligands. Okay, now how to do this kind of thing? So basically tell me the first point. You have to identify the small group in the left hand side. So this is the double bond, this is your right hand side, this is your left hand side. So now I am starting to identify. So this is your hydrogen, so that means what? This is your small group. Now how to identify medium group and large group? So see how many carbon atoms are there. 1 2 3 4. Right hand side you have only 4 carbon atoms. If I go to left hand side, 1 2 3 4 5, I have 5 carbon atoms. So that will be what? That will be your large group, and right hand side the alkyl chain will be your medium group. Clear? How to check it?
Yes.
Clear? Don't consider this hydrogen as small group, otherwise it will be wrong. Okay, I clearly mention here that number 1 point, that small group should be at left side. Okay, left hand side. So if you consider this hydrogen, then it will be wrong. Okay, so no need to consider this hydrogen, you can do from here. So small to medium to large, so you just rotate like this. small to medium to large. What motion it is? Clockwise, na? Clockwise motion. What reagent you are using? DHQD. So more letters you have. So more letters means what you will get? Above the plane. Okay, top. So above the plane you will get. So the product will be basically like this. First of all, draw the skeleton. What you have. So now here put one OH group here and another OH group here. So this is the skeleton we have. Clear? Clear? Anything doubt? Isa, Sita, Smita is there. Nayana, Sampriti. Clear?
Sure, sir. Yes.
All of you clear?
Yes, sir. Yes, sir.
Okay. Now do this by your own. Suppose you have this, 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 this. CO280. Okay. So here I am giving write down the product. Tell me what is the product?
First one is about
DHQ will be what?
sorry, below the plane. First one. Second one is above the plane.
Okay. So first of all you just see here you have hydrogen, so that is your small group. Okay. This side you have only CO280, so one carbon, this is your medium group, and this side you have 1 2 3 4 5, so that one is your large group. So you just move small to medium to large. Okay. So what motion it is? It is your clockwise motion. So if you have clockwise and you are using this DHQ reagent, so that will be what? Less number of letters, so that means below the plane, right? So that will be what? Below the plane. This is also what? Below the plane. Now if you are using DHQD, so more number of letters you have, so that will be what? Above the plane. Okay. Okay, correct. Fine. Now suppose next you have this 1 2 3 4 5 6 CO2 double bond is there. Do this.
The first one is below, second one is above.
First one is below.
Second one is above.
So here hydrogen is small group, right? This is your small, CO2 will be medium, and this will be what? Large.
Large.
So small to medium to large. This is which motion?
Yeah. Anti.
Anti-clockwise, na?
Mm.
This is your anti-clockwise motion. So if you have anti-clockwise motion, that time it will be opposite to your clockwise. Okay. So if you have anti-clockwise, that time with this DHQ reagent, you will get what? Above the plane, not below the plane.
Above.
Okay, above the plane you will get. And if you have more number of letters, that time usually we get top, but if you get anti-clockwise, so that time we will get bottom. Okay, opposite to your clockwise. Okay, so this OH is below the plane, and here also the OH will be what? Below the plane. That's it. Is it clear?
Yes, sir.
All of you clear? Okay, write it down. Done. Done, right? Okay, fine. Now suppose you have this. This topic, this surplus asymmetric dihydroxylation, that actually you will find better in Carothers. Okay. In Claydon also you will get. So any book you have, you just check one time. Okay. These examples I have taken from there. So yeah, you can just check. Okay, fine. Now this thing. So here you can't decide actually. Okay. First of all, you just place the hydrogen here. So that is your small group. Now if you see right hand side, you have 1 2 3 4 4 atoms, and here also you have left hand side also you have 1 2 3 4 4, right? So you can't actually decide which one is medium and which one is large, right? So now comes your fourth point, this point where I have fourth point. Yeah, if can't decide, so that time you have to follow which rule? Clockwise rule. Okay, so if you are not able to decide, okay, so that time you have to follow the clockwise rule. So according to clockwise rule, if you have DHQD, what you will get? Above the plane. So that you have to do. So basically, yeah, here you just place one OH, okay, and one OH will be here. That's it. Okay, fine, understood. Any doubt from this topic? Hmm? Okay, write down DHQD. None of you actually asked me, sir, what is DHQD? What is DHQ? So DHQD is actually AD mix beta. Okay, and DHQ is actually your AD mix alpha. So these are the two reagents you have. Structure will be very bulky structure. Okay, AD mix beta and AD mix alpha. I am showing you here. That will be better. DHQD and DHQ reagent structure. So yeah, you can see these are very bulky reagent actually. So these are chiral ligands used in surface asymmetric dihydroxylation to create chiral diols from alkenes. Okay, so this DHQ is basically what? This is your AD mix alpha, and DHQD is basically AD mix beta. So in interview they will not ask you to write down the structure, okay, because these are very bulky structure, but yeah, they will ask what are the nature of this ligand, so you have to mention these are chiral ligands. Okay, and what you will get chiral diols. Okay, so that's why I am saying that please at least one time just go through your Clayden or Carruthers book, so you will get some extra idea from there. Okay,
So
yeah,
this reaction is chiral catalyst or chiral auxiliary?
just a minute, huh? Yeah, ask me what you are saying.
Is this reaction type
Hmm.
chiral auxiliary or chiral catalyst?
Chiral catalyst.
Okay.
Chiral catalyst. This is not your chiral auxiliary. Okay. Done.
Yes.
Okay, basically I am saying for the PhD, okay, who will give interview in PhD, they just look these books. Okay, MSc, no need to worry, they will not go in that detail. Okay, they will basically ask from BSc, but for PhD who actually will appear in the interview for PhD, they have to check. Okay, they can ask. If you mention reagent chemistry, they can ask anything. Okay, okay, fine. Now next we have Bayer's reagent. Bayer's reagent. Okay, so what is Bayer's reagent? So Bayer's reagent, KMnO4 potassium permanganate in presence of OH minus. Okay, OH minus. So potassium permanganate in presence of OH minus, and that is basically known as what? Oxidizing agent. Okay, this is basically an oxidizing agent. Okay, so what happened basically? So suppose write down in acidic medium, what will happen in acidic medium? In acidic medium, over oxidation will happen. Okay, over oxidation. So you have to check with KMnO4 what they are providing. If they are providing OH minus, you have to do normal oxidation. Okay, this is OH minus means what? This is your basic medium. Acidic medium means with KMnO4 you are providing what? H plus. So that you have to check. In acidic medium it will get over oxidation. So what you have basically, this is what? MnO4 minus potassium permanganate, right? So manganese is present in plus 7 oxidation state. Now it is actually reducing to what? Manganese 2 plus. Okay, so it takes 5 electrons and it is reducing to manganese 2 plus. So manganese itself reduces, so that means for the others it is doing oxidation. Okay, so this is your acidic medium. And if I talk about a basic medium, okay, so write down in basic medium, in basic medium what is happening? So you have manganese MnO4 minus, same thing. So here manganese is also present in plus 7 oxidation state, but here it is reducing to manganese plus 4, so that means MnO2. Okay, MnO2, you can write down this is your MnO2 and manganese plus 7, so that means what, this is your MnO4 minus. Okay, so in basic medium basically manganese plus 7 is coming to plus 4, but if you do acidic medium that time it will do over oxidation. Why? Because from plus 7 it is coming to the lowest oxidation state, plus 2. Okay, clear? So this is the two things you have, KMnO4 OH minus and KMnO4 H plus. Okay, we will see one by one. So first of all let's see the mechanism how the dihydroxylation is happening by your basic medium. Okay, so suppose you have this molecule, okay, and here I am using this manganese double bond O, double bond O, double bond O minus. This is your MnO4 minus, right? Right?
Yes.
What will happen? Tell me. What will happen? You guys are also doing mechanism for a month. Now tell me what will happen? How it will attack?
Negative charge will attack double bond will attack O again.
So basically first of all O minus, right? So it will go to there. Oxygen is donating the negative charge to this bond. Automatically this bond will break. Okay, and it will attack here. Okay, when it attacks here the electrons will break like this, or it will flow like this, and it will come to this oxygen center, and ultimately it is coming to your manganese center. Okay, so now how it looks? So basically you will get like this oxygen. Okay, here also you have oxygen, manganese, this double bond is now becoming single bond, and here you have double bond O, double bond O. Clear? Now what are the reagents we are using? We are basically using what? KMnO4 in presence of OH minus. In basic medium we are doing this. So what will be the next step? So OH minus will directly attack on the vacant d orbital of your manganese. This bond will break. Similarly, you have another vacant space, so OH minus can attack from this side also. This bond will break. So ultimately what you will get? Initially you will get like here O minus. When you are doing some reaction, so that means some amount of water always will be present, so automatically it will be hydrolyzed, OH. Okay, and what is the byproduct here? OH, okay, double bond O, okay, and yeah, double bond O. Okay, that is the byproduct. Is it clear? Mechanism is clear. Any doubt from the mechanism? Nayana, Sita?
Clear, sir.
Clear, right? Sampriti, clear?
Yes.
Clear, right? Isa, clear? So this is your mechanism of dihydroxylation. Okay. Now the second thing comes that suppose you have this. Okay, same molecule you have, same molecule. Here I am giving this reagent KMnO4 in presence of H plus. Okay, so when I am giving acidic medium, so acidic medium means what? Acidic medium means you have to remember over oxidation. Okay, so over oxidation. So first of all you just do like that. First of all, if you have KMnO4 OH minus, what you will get? You will get dihydroxylation, so one OH to this bond and one OH to this carbon. That you will get, na? Hmm?
Yes.
Hmm. Now over oxidation means another OH will come to here. Okay. Another OH will attach to this carbon atom, and when another OH is coming, so this bond will erase. Okay, this bond will break. So ultimately you are getting this compound. This is actual meaning of your over oxidation. So if you have KMnO4 OH minus, you just attach 2 OH to the 2 carbon atoms. If you have KMnO4 H plus, you have to attach 2 oxygen at 1 carbon atom. So overall you have to attach 4 OH. Okay.
So how is it happening? Double OH?
Double OH, that it has actually different mechanism. Okay, I will show it. I will show it, no need to worry. But first of all, yeah, just check what I am getting. First of all, let me complete it. Okay, now if I have, this is an intermediate. Okay, this is not at all stable. Why? If if one carbon has 2 OH, so what you will get?
You will get
Water will release, right? So release water from here and release water from here also. Okay, you can release like this or you can sew like this. Okay, you can sew like this. Hydrogen is back, OH is leaving. Okay, here also hydrogen back, OH is leaving. So what I am getting? I am getting double bond O, double bond O. Okay, so you are getting this dihaldehyde compound. Dihaldehyde compound. Now this is also an intermediate. This is not at all. Aldehyde is also not stable. Okay, so that will ultimately oxidize to your what? In presence of acidic condition, if you are using some acidic medium, so in presence of acidic medium, the aldehyde will ultimately oxidize to what? Carboxylic acid. So that will be your product. Okay, that will be your product. Clear? Tell me any doubt.
Yes.
Any doubt? Any doubt?
No, sir.
No, right? Okay, now basically how you will get, so this has actually different mechanism. Okay, so this acidic medium you have to solve like this. So suppose this is your double bond. Okay, here I have manganese, double bond O, double bond O. Here you have O minus, double bond O. So what will happen? So basically you can show like this. This double bond is attacking on oxygen. This oxygen is attacking here. Syn addition. This is also your syn addition. Okay, this addition is also your what? Syn addition. Syn addition. Syn addition. Now this is also attaching with oxygen. Okay, here you have manganese O minus, double bond O. Clear? Now what will happen? So now basically if this negative charge donates the electrons to this bond will break, this bond will break, and this bond will also break. Okay, so this is actually known as your oxidative cleavage. Okay, oxidative cleavage. Oxidative cleavage. Okay, and if you do this, what you are getting? What you are getting? Tell me. See here, you are getting what? Double bond O, and here also you are getting what? Double bond O, and with that you are getting what? MnO2, double bond O, plus 4 oxidation state. Clear? Clear? Mechanism is
Yes,
clear?
yes,
Is that clear? So this is the mechanism for your oxidative, okay,
We're
chem.
getting MnO2 for acidic or basic? We wrote basic for the previous one.
MnO2 you are getting initially, then it will also reduce to manganese 2 plus, okay. That will do some inorganic reaction, huh? That is not your final intermediate. It will also reduce to manganese 2 plus, okay. But initially you will get this manganese MnO2, okay, because this is also not stable, na. This aldehyde will also oxidize to your what, carboxylic acid, okay. This is also oxidizing to carboxylic acid. So when the aldehyde is oxidizing to carboxylic acid, that time this MnO2 is reducing to your manganese plus 2, okay. Clear? Initially it is present in Mn4 plus when you are getting aldehyde, but in presence of H plus, in presence of acidic medium, what will happen? The aldehyde will oxidize to your carboxylic acid, okay. So basically water will attack there, and here it will reduce now to manganese plus 2. Clear?
Clear.
So these are the Bayer's reagent, okay. We have two method: basic medium, this mechanism you follow; acidic medium, this mechanism you follow. But how to get the product, that is very simple. If we are talking about basic medium, so that time you just attach 2 OH, and if you have acidic medium, you just attach 2 OH to the both carbon atoms, then you have to remove water, you will get aldehyde, dialdehyde, and then you will get dicarboxylic acid, okay. So mechanism I have shown. Now we will practice questions, okay. So now let's do the questions. So suppose you have this. So here I am giving KMnO4 in presence of OH minus. Tell me what will be the product.
Diol.
Diol.
Okay.
Stereochemistry. Stereochemistry of diol will be what?
below the plane.
Below the plane, right? Because methyl is already present above the plane, so osmium tetroxide, sorry, MnO4 will approach from the opposite
Below the
plane,
plane.
below the plane. Okay, fine, good. Now what about this? This, 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 this. Here I am using KMnO4 in presence of OH minus, okay, and here I have KMnO4 in presence of H plus. Do it.
In basic medium, there will be syndiol form below the plane.
Here I have not mentioned any stereochemistry, so you can show below the plane, above the plane, anything, okay. I have not shown anything stereochemistry. If I am showing, suppose this is above the plane, so that time definitely you have to show below the plane, okay.
Okay.
Okay, so I am writing like this only. I am not showing any stereochemistry, but again I am saying if I am showing like above the plane, so that time OH will be below the plane. Fine. What about this KMnO4 H plus?
You have carboxylic acid with or cyclization removed.
Cyclization, no, cyclization will not take place.
No, it's over. Cyclization is gone.
Hmm. So first of all, how to do? First of all, you do oxidation. So oxidation means what? Oxidation means you just attach two OH here. Right, this is your oxidation. Now you have to do over oxidation. So over oxidation means what? You have to attach another OH here and another OH here, and you just remove this bond. So this is meaning of your over oxidation. Okay, now what you have to release?
Water.
Water you have to release. So basically if you release water from here and here also you can remove water. So what I am getting? So here I have double bond O, and here I am getting what? Double bond O. So this is what? This is your ketone, and this is what? This is your aldehyde. Okay, if nothing is there, so that means keep in mind hydrogen is there. Okay, so aldehyde. So now what will happen? Aldehyde is not stable. So if you do over oxidation of that, keep in mind ketone will not get oxidized. Ketone will remain like that only. Okay, ketone will remain like that only. Okay, but this aldehyde will oxidize to what? Carboxylic acid, CO2H. Okay, so always keep in mind if you have aldehyde and ketone, aldehyde will oxidize to carboxylic acid, but ketone will not oxidize. Ketone will remain intact. Clear? Is it clear?
Yes, sir.
Nayana, clear? Any doubt? Let me check.
Yes, sir.
Clear, right? Okay, fine. Okay, now suppose you have this. Okay, here I am giving KMnO4H plus. Write down the product, what you are getting. Done.
Acetone and acetic acid.
Yeah, acetone and acetic acid, correct. So initially what you have to do? You just attach two OH, right? So like that OH plus what? Plus here I will get CH3, attach two OH here. So now release water. If you release water, what you will get? So here I am getting acetone, and if you release from water from here, so what I am getting? I am getting acetaldehyde, CH3 CHO. So ketone will not oxidize again, ketone will remain intact, but this aldehyde is not that much stable. Okay, so it will oxidize, further oxidize to your carboxylic acid. When you will do reactions in lab also, okay, if you have aldehyde, some aldehyde compound, so you have to actually do the next step. Okay, when you will do that time you will know aldehyde is very like not very unstable, but yeah, you cannot keep it for 1 to 2 days like that. You have to do the next step reaction, otherwise it will decompose. Okay, fine. Now suppose this is one aromatic ring and here you have CH3 alkyl group. Okay, so here I am using KMnO4 H plus. So this is basically 11-12 reaction. Okay, if you have one any alkyl group is present with your benzene ring, basically aromatic ring, any alkyl group is present. Okay, so that time you will get what, the alkyl group will be oxidized. Okay, just a minute. हाँ बोलो. हो गया. देख, रुको रुको, आधा घंटा है और देख. ठीक है, बैठो बैठो, थोड़ा बैठो. हाँ, रूम जाओगे, क्या करोगे? इस देख, जाता हूँ. रुको पढ़ा देता हूँ. हाँ, okay, so if we have any alkyl group present with your benzene ring, so what will happen, it will oxidize to your carboxylic acid. So it will oxidize to your carboxylic acid, CO2H. Now keep in mind this alkyl group, okay, this alkyl group should be primary and secondary. Okay, primary and secondary. But if you have tertiary alkyl group, okay, tertiary alkyl group, that time it will not oxidize. Okay, so if you have primary and secondary alkyl group, that time it will oxidize to your carboxylic acid, and if you have tertiary alkyl group, that time it will not oxidize further. Okay, fine.
Yes, sir.
Okay.
So can you give example of secondary?
I am giving. Suppose you have this. This is isopropyl group is attaching with your benzene ring. Do it. हाँ, नहाओगे ना तुम?
चिट्टू को क्यों ऐसे कर रहा है?
क्या कर रहा हूँ मैं? वो कुछ नहीं, वो ठीक है.
उसको कर रहे हैं.
कुछ नहीं कर रहा हूँ.
जिम गया?
हाँ, देख नहीं रहा.
ऐसा लग रहा है.
हाँ, ध्यान से जाना.
सब लेके आना.
अरे हाँ रे, लेके आऊँगा, चिंता मत कर. ध्यान से जाना. सखी क्यों लाया हो ना? हाँ. Yeah, so what will happen if you have isopropyl group, any alkyl group you can give, you can attach any alkyl group, so that time it will oxidize to your carboxylic acid only, CO2H. Fine. Now suppose I am attaching here tertiary butyl group. Okay, tertiary butyl group, and you are giving same reagent KMnO4 in presence of H plus. So here you will get no reaction. No reaction. Clear? Clear? basically in interview they can ask you that what is the mechanism. So mechanism I will show. Okay, no need to worry. But actually what they are asking that why in tertiary, why you have, if you have 3-degree alkyl group, so that time why you are not getting any product. So you have to say, that sir or ma'am, you have hydrogen here. Okay, if you see benzylic hydrogen is present here. Here also you have hydrogen. When you are attaching some secondary group, that time also you have hydrogen. But if I have tertiary alkyl halide, that time I have no hydrogen. So that hydrogen is not migrating to your manganese center. Okay, when I will show the mechanism, that time it will be clear. I will not show it today. Okay, but yeah, I will show it. Okay, so that time it will be clear. So that hydrogen is not migrating here because you have no hydrogen here. So that's why it is here you are not getting any reaction, because manganese is present in plus 7. So hydrogen will migrate to this manganese center, then only my manganese will reduce. Okay, so if you have no hydrogen, so that means no hydrogen donation is possible and manganese is not reducing. Okay, okay, so like that only. Now suppose you have this, suppose I have this KMNO4 H plus. Tell me the product quickly.
Cyclohexanone
Hmm.
and formic acid.
Cyclohexanone, okay, plus formic acid. Correct. So if you do one time oxidation, you will get what, OH. Then you just do an over oxidation, so you will get formic acid plus cyclohexanone. Correct. Okay, now this question try to do. So basically in exam they will not give you that much easy question. This is an exam question. Okay, this one is your exam question. Do it. Tell me the product.
What to Daiquito?
No. Check it. Here you have to use the concept. Check it. First of all, tell me here, if you have this kind of ring, bicyclic system, okay, or heterocyclic system, so that time you just tell me which ring is electron rich here.
Sorry?
Which ring is electron rich and which ring is electron deficient?
Electron rich is the heterocyclic one.
No. Here nitrogen lone pair is in conjugation with the double bond. No. So plus M effect is not there. Here you will have minus I effect. If the lone pair, any lone pair is in conjugation with your double bond, or suppose it is taking place in conjugation, that time only you can say that sir, resonance is applicable there. But if the lone pair is not in conjugation, that time minus I effect will be there, minus I. Okay, not your plus M. Plus M is not present here. Here you will get minus I effect. So that means it is withdrawing electrons. Okay. So basically this heterocyclic ring, due to its electronegativity, it will be electron deficient. Okay, and this benzene ring will be what? Benzene ring will be your electron rich. Okay, if your lone pair is not in conjugation, that time it is not electron rich, it becomes minus I effect, so that means electron deficient. Okay, so here the benzene ring is becoming electron rich. And what about your reagent? Manganese is present what? Plus 7, so that is what? Electron deficient or electron rich?
Deficient.
Electron deficient. So now tell me from your concept that if your reagent is electron deficient, which ring will react? Electron rich or electron deficient?
Electron rich.
Electron rich will react. So that is the thing you have to check. Okay, or you have to take care. So if your reagent is itself electron deficient, so that means the electron rich ring will react, not the electron deficient. Now you can do. So if you are doing this, so first of all do oxidation, then we will do over oxidation. So first of all do oxidation. If I do oxidation, what I will get? So attach OH here, OH here, OH here, OH here. This is your oxidation, right?
Yes.
Right. Now do over oxidation. So if I do over oxidation, what I have to do? I have to attach another OH here, another OH here, another OH here, another OH here. And if you are attaching, this bond will break, this bond will break, this bond will break. So ultimately what we are getting this kind of thing. See, OH OH, OH OH, okay, plus what you are getting? This side also you have what? OH OH, here also you have OH OH. So after bond breaking you are getting this. So ultimately what you will get? You have to release now water. So if you release water from here, what you are getting? What?
Formic acid.
Initially you will get formaldehyde, right? CH2 double bond O, right? Oxygen double bond what? CH2 plus what? Here also you are getting what? Oxygen double bond CH2. This is your formaldehyde. And here also you can release water. So you will get what?
Acid.
This is your pyridine, right? So pyridine, initially you will get here CHO. Here also you will get CHO. And aldehyde is not stable, so aldehyde will do over oxidation. So ultimately you will get 2 formic acid, because you are getting 2 formaldehyde derivatives. So you will get 2 formic acid plus what? Plus you will get this pyridine derivative, carboxylic acid derivative, CO2H. Here also you will have CO2H. Is it clear?
So the double bond is where the cleavage happens, right?
Which double bond?
Until now, oxidative cleavage was happening where the double bond is. But here you have not done only in double bond oxidative cleavage. You have done 3 times cleavage. But there were only 2 double bonds.
3 times cleavage means it's not like that. Suppose you are adding one more OH, na? So that means what? Carbon is maximum 4 valence, na? So one bond has to break. Initially you are getting, I am attaching OH here, OH here, OH here, OH here. Now when you are doing over oxidation, so another OH is coming. So you have to break this bond because carbon has maximum 4 valency. Clear?
Like if we do this same thing for 1,3-diene, this will not happen.
1,3-diene.
Yeah.
1,3-diene you are asking, okay?
Yeah, like 6-diene, yeah.
Like this?
Yeah, so it's similar to what is there in the carbocyclic ring. But if you do oxidation of this, you will not get what we have got here. You will get or one
No,
to die. No.
initially you will get this, na? If you do this, so initially you have to attach OH here, OH here, OH here, OH here. So this is oxidation. Now over oxidation will take place. So you have to attach another OH here, another OH here. So that means carbon 4 valence is already filling. You have already one hydrogen there, na? You have to attach one OH here, one OH here. So you have to break this bond, this bond, this bond, like that.
No, but how are you breaking the middle bond? Only the
Because
top and bottom.
carbon has to like carbon has 4 valency, na? You can do with mechanism also. You will get the same thing. I have shown you the mechanism, na, here. This mechanism. Here also see how I am breaking the bond. Because this oxygen has the driving force. This actually pushes the electrons towards this. Then this electrons going to here. So this electron density is actually helping to break this sigma bond. Here also you have a sigma bond. How you are breaking this?
That's what I'm saying. It's happening only where there is a double bond. But in the reaction that we were doing, it's happening where there is a single bond. That should not be possible, no?
Okay.
That's what I'm saying.
This single bond you are asking. Okay, fine.
Because the double bond will react with KMnO4 and form that cyclic intermediate. But the single bond won't.
Okay, I will check that, huh?
Yes.
I will check that. Okay, I have break this bond also, na? Okay, okay. Okay, sure, I will check that. Okay, fine. So next what we have? Next we have Woodward reagent. Okay, Woodward reagent. So what is Woodward reagent? So Woodward reagent is this silver acetate, okay, in presence of iodine, in presence of water. So they ask many questions from this reagent, Woodward reagent, and the next reagent also, previous reagent. So okay, let's start Woodward reagent. So first of all, write down one point. You will get syn dihydroxylation. Okay, syn dihydroxylation you are getting. Okay, syn dihydroxylation. So what is the mechanism? So here also you have alkene species double bond. Now in presence of iodine, so basically iodine means this, na? So double bond will attack iodine. This iodine leaves. Iodine also has lone pairs, so iodine will attack from the lone pair. So what I am getting? So I will get this kind of thing, cyclic 3-membered iodinium species I will get. Okay, cyclic 3-membered iodinium species you will get. Next you have silver acetate, so silver plus, and here you have OAC minus. So now OAC minus is attacking on this carbon center. This bond will break. Okay, so what I am getting? What will be the plane of symmetry? From which face it will attack? Oxygen, then what? Okay, OAC means what? C double bond O CH3. Okay, this is your OAC, and above the plane you have iodine. Fine. Clear? This is cyclic 3-membered ring is forming above the plane, so OAC minus has to attack from the opposite face, from the below the plane. Okay, then you are getting this kind of anti-product. Now if you have silver plus, so iodine has what? Iodine has lone pair, right? Iodine has lone pair, so iodine will donate the lone pairs in the vacant orbital of silver plus. Okay, so what I am getting? Oxygen, write down like this, C double bond O CH3, and this side you are getting what? So iodine is donating electrons to silver plus. Iodine is donating electrons, it will be positively charged. Silver is taking electrons, it will be negatively charged, but already it has a positive charge, so positive and negative, it is becoming what? Neutralized. Right? Now what will happen? See, this oxygen has lone pair, this oxygen has lone pair, so it will attack here, and this is a very good leaving group because it contains positive charge, so it will leave from here. Okay, so what I am getting? Oxygen, here you have carbon, CH3, this side you have double bond O, this, and oxygen is donating electrons, so it will be again positively charged. Now tell me, why this oxygen is not donating electrons? It has also electrons, na? Why this is not attacking here? Why this oxygen is attacking here?
Conjugation with double bond.
Conjugation, correct. Conjugation is the reason. So basically this oxygen lone pair is in conjugation with this double bond, correct. Okay, so this small thing you have to notice. Okay, when you are doing some mechanism, you have to clear all the things. Okay, don't do it like blindly. You have to think it, why it is happening, why it is not happening. Okay, fine. So this is clear. Okay, next, what reagent I have given you here? See, AgOAc, silver acetate, iodine, and next is water, right? So now water rolls comes. Now water will come. Okay, now it will attack here on the electrophilic carbon center. Oxygen is getting neutralized. So what I am getting here? Oxygen, here also you have oxygen, carbon, CH3, and here I will get OH. Okay, OH. Now tell me next step, what will happen? Next step, what will happen? Anyone? Oxygen will donate the lone pair, this carbon oxygen bond will break. Okay, so what I will get? So here I am getting what? O minus, and here you will get oxygen, carbon, double bond O, H, positive charge, CH3, right? Now again you have another equivalent of water. Okay, see, I am showing one thing. You have O minus and here you have what? OH plus, right? So this O minus can take up this proton, and if it takes up this proton, what you will get? What you will get? This thing, na? So you can show like that also, or you can directly writing like this, like hydrogen is coming, it is coming to the oxygen center. You can show like that also. Clear? Now you have another water, so water will attack where? On the carbonyl carbon. Okay, so water will attack on the carbonyl carbon, this bond will break, it will come back, ultimately this bond is breaking. So what I am getting? I am getting syndiol, OH, and what is the byproduct? Okay, byproduct also, if you do some mechanism, always check the byproduct, because sometimes they ask what is the byproduct of this reaction. Not all the professors, but some professors are very interested with the byproduct, so that time they ask. Okay, but yeah, this is your main product. Okay, this you have to know. Syn dihydroxylation you are getting. Any doubt in the mechanism? Tell me. Sita, Nayana, Isa, Sampriti. Am I audible?
It's a audible, sir.
Clear?
It's a clear, sir.
Clear, right? So syn dihydroxylation will happen. Now let's do some questions. So suppose I have this. Write down the product. Tell me the product. Which system it is? First of all, tell me which system it is.
It will be syndiol above the plane and osmium syndiol below the plane.
Osmium tetroxide you will get?
Syndiol up below the plane.
Below the plane, correct. And if you do with this Woodward reagent, you will get above the plane. So first of all, this is your trans-decalene system, na? Trans-decalene system. So draw it in your chair form. See, in exam basically they will give like this cyclic form. You have to do it by yourself. So that much practice you need, so that you are able to understand that I have to draw it in chair form. Now methyl is in above the plane, so CH3 will be here. Hydrogen is in below the plane, so that will be here. Now here you have double bond. That is the thing. Now tell me, if you, first of all I am talking about silver acetate. So what is the, if you check the mechanism, what is the first step? Iodination. Okay, so now tell me, iodination will happen from which phase? Above the plane or below the plane? Nayana, tell me, Nayana. Below the plane, right? Why from below the plane? Because above the plane you have this bulky group, methyl group is there. So this iodination is happening from below the plane, like that. Okay, so iodination is happening from below the plane. So next step is what? Next step is just same thing. Okay, OAC minus will attack from this side. Okay, switch off the mic, huh? Otherwise that yeah, thank you. Otherwise when you will see the recording, that time that noise will come, huh? Okay, fine. Now what I have, CH3, okay, hydrogen. So basically now you are getting here oxygen, C double bond O, CH3, okay, and this side you have iodine. Now this oxygen lone pair will attack here, iodine will leave. So basically now it comes to above the plane, so you will get, okay, same mechanism you can do. Okay, same mechanism, you will get a thing like this. I am drawing oxygen, carbon, here you have CH3, double bond O, positive charge. So basically you are getting this. Now water will attack here, okay, and then the rest of the mechanism. So you can see the oxygen is already coming to the above the plane. So that means here the product will be this syndiol you are getting, but above the plane. So here you have methyl, okay, here you have hydrogen and OH are coming from above the plane. And if you use osmium tetroxide, what will happen?
Below the plane.
Below the plane,
Right,
because
I think.
osmium tetroxide now you have to approach. So osmium tetroxide cannot approach from above the plane, so it will approach from which side? From below the plane. So you will get here below the plane compound. Clear to all?
Yes, sir.
Clear, right? They are asking repeatedly question from this Woodward reagent. Next you have Prevost reagent. So they are asking so much questions from this topic. Okay. Okay, fine. So this thing is clear. You have written, all of you?
Yes, sir.
Should I proceed? Okay. Do it. Exo endo product you will get. Tell me where you are getting exo, where you are getting endo.
Exo for osmium, endo for the other one.
So here you have hydrogen. So if you have hydrogen, so that means what? Osmium tetroxide can will approach from this side, okay, from above the plane, okay. So osmium tetroxide will approach from above the plane. So what I am getting? I am getting here like this. This is what? This is your exo product. And if you are giving this Woodward reagent, so that time above the plane what you will form? Above the plane that cyclic iodinium will form, okay. This thing will form above the plane. So if iodinium is forming above the plane, so that means what? OAC minus will approach from below the plane, okay. When it is approaching from below the plane, so that means the dihydroxylation will take place from also below the plane, and this is what? This is your endo product. Clear?
Yes, sir.
Write it down. Done.
Yes, sir.
Okay, suppose next you have this. Same thing, but you have methyl, okay. Same thing, but you have methyl. Now tell me. What? If you have methyl, methyl is present in the bridging position, that time what will happen? X or endo?
Below.
So that time the osmium tetroxide will approach from below the plane, because already you have methyl group which is bulky enough. So osmium tetroxide has to it cannot approach from this side, it has to approach from below the plane, okay. And if you have Woodward reagent, so that time cyclic iodinium will form from which plane?
Below.
Below
Below
the
the
plane, so that means OAC minus, okay. I am drawing here
approach above the plane.
cyclic iodinium, yeah. So the cyclic iodinium will approach from below the plane, and OAC minus will attack from above the plane. So that means the OH you will get here. So this is your what?
Endo.
Endo
Second
product.
one. Exo.
This is is your exo product. Which one is more stable? Which one is more stable, endo or exo? Here
Endo, sir.
endo. Why?
Because there is a minimum repulsion.
Yeah, minimum
Steric
repulsion.
repulsion. Yeah,
Yeah.
steric repulsion.
So you have two bulky methyl group here, which is also above the side. So here steric repulsion is there. Here they are in the downside. So that will be your more stable due to minimum repulsion or minimum steric hindrance. Okay,
Yes.
fine.
Yes, sir.
Okay, so that's it. Okay, tomorrow we will finish the organic chemistry. Okay, I am trying to finish by tomorrow because some of you have already interview dates. Okay, so I am trying to finish by tomorrow this reagent chemistry. Okay, so I will message the timing in the group. Okay, and yeah, any doubt up to this Woodward reagent? So we have what we have discussed today. Today we have done Sharpless asymmetric dihydroxylation, Bayer's reagent and Woodward reagent. Three reagents we have done. Any doubt from here? Yeah, we have started from here. Sharpless asymmetric dihydroxylation, you have to remember this trick. Then we have done Bayer's reagent. Okay, Bayer's reagent. Here you have Bayer's reagent. We have two conditions: acidic medium, basic medium, and at last we have Woodward reagent. Okay, and I will check why this sigma bond is breaking. I will check that. Okay, Woodward reagent. Fine. Any doubt? All of you? Any doubt?
Cheers.
Clear, right? Okay, fine. Okay, bye. Okay, tomorrow we will
Bye.
meet again.
Bye.
Okay, thank you.